Alright, in this video we'll be going through the 2023 Mechanics Exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself, and once you're finished with the question or get stuck, unpause the video and see how I go about getting the answer. Alright, so in this first question we need to draw a vector diagram to identify the net force that is responsible for the car going around in a horizontal circle, okay? And obviously from our circular motion we should know that if a car is going in a circle, that means there must be a force accelerating it towards the center of the circle, and so that is our net force right here, okay? F net. There we go. So the banked curve has a radius of 0.75 meters, and then we need to calculate the angle of the bank as the car goes around the banked curve at 1.55 meters per second. Alright, so there are two methods to solve this problem. The first method is to use a vector diagram. So if we just draw out our diagram right here, simplified, okay? Right, we have an angle right here, theta, that we're trying to find. We have our weight force acting downwards, and we obviously know we have a FC towards the center, and we would have a reaction force, or our normal force, that is perpendicular to the surface, okay? And so from here, we can construct a vector diagram where we have our weight force acting downwards, our normal force acting up here, and our FC like so. And then this should form a closed loop like that. Okay, so this is our FC, our FW, and our Fn, okay? Now, theta is this angle right here, okay? Now, the reason why I know it's that angle and how I like to teach it is if we look at our reaction force, okay? Our normal force. If we imagine this situation, but the angle is slightly less, so let's make the angle slightly less like this, okay? And we can call this angle phi, okay? We have our weight force, our FC, and then our normal force, which will be like this, okay? As you can see, our normal force for this diagram B and this diagram A, okay? So our normal force for diagram B is slightly more vertical, okay? And if we make a vector triangle for this, we can see, weight force down there, a slightly more vertical normal force, and our FC. And this is our angle phi. As you can see, when we make our banked corner less of an angle, the angle in our vector diagram also decreases. So, as this is our Fn, if our Fn in our diagram also becomes more vertical, you can see that the Fn in this diagram also becomes more vertical. And the angle that's becoming smaller is this angle, okay? And the opposite is obviously also true. If we make this theta value larger, so it's more of a banked angle, our normal force is going to come more horizontal, and therefore this is going to come out here, and as you can see, our theta value would increase, okay? So that is how we know that this is our theta value. So because we know that is our theta value, we can calculate our weight force, and that is obviously mg, where our mass is 0.12 times our acceleration, which is 9.81, and that gives us a value of 1.1772 newtons. And we can calculate our Fc as mv squared over r, where our mass is again 0.12 times our velocity of 1.55, and that's obviously squared, all over our radius of 0.75. And that gives us an Fc of 0.3844 newtons, okay? So as you can see here, we have our adjacent side here and our opposite side here, so we can use our tan relationship, okay? And so obviously inverse tan, opposite, which is our Fc, all over our adjacent, which is our weight force, and that is going to be equal to our theta. And so plugging in our numbers, we have our Fc of 0.3844 all over 1.1772, and that gives us a theta value of 18.1 degrees. There we go. So now for our second method, let me draw out that diagram once more. Okay, we have our theta here, we have our car over here, weight force coming down, normal force up this way, and we have Fc over here, okay? As we know, our Fc is not a force in and of itself, it's a net force, right? We got that from our first question, right? This is the Fc, and therefore it's a net force, okay? And so therefore, as Fc is not a force in and of itself, and it's a net force, it has to be provided by another force. And we know that it's provided by the normal force. If you don't know that, watch my horizontal circles video in my mechanics playlist, okay? So Fc is provided by the horizontal component of the normal force, okay? And so the horizontal component of the normal force is the normal force cos theta, okay? And also in my horizontal circles video, I also established that the vertical component, which is Fn sine theta of the normal force, is equal to the weight force, okay? And so as I said previously, the horizontal component is the centripetal force, right? And therefore, this is equal to mv squared over r, and this is equal to mg. And so therefore, we can say that Fn sine theta all over Fn cos theta is equal to our weight force all over our centripetal force. Now we should know from our math courses that sine theta all over cos theta is equal to tan theta, okay? And so therefore we can say that tan theta is equal to our weight force all over our centripetal force, okay? And therefore theta is equal to the inverse tan of our weight force all over our centripetal force. And as you can see, this is essentially what we had up here. And obviously plugging in our numbers, we get the exact same theta value. Okay, so explain why a person feels heavier at the bottom of the loop compared to the top of the loop. And we need to draw on the diagram to label the forces at the top and at the bottom. Okay, sweet. So again, if you don't understand this video, I highly recommend watching my vertical circles video on my mechanics playlist. But we should know that the feeling of weight comes from the size of our normal force. So the normal force gives us the sensation of weight, because that is the force that's accelerating us upwards, okay? And that is why when we're in space, for example, even though we have a weight force, because there's no normal force acting on us, we actually don't feel like we have weight. And so at the top and at the bottom, we obviously have a weight force acting downwards, okay? This weight force has to be equal in both cases because the cart obviously does not change in mass as it goes up the vertical loop, right? The mass stays the same, so therefore the weight force has to remain the same, okay? What does change is the normal force, okay? As we discussed in the previous question, in order to have a centripetal force, which in this case there is going to be a centripetal force because we're in a circular motion, okay? In order for there to be a centripetal force, there must be a net force. Now, we know that the net force has to act towards the center of the circle. So let's take this bottom scenario. The only force that's going to act towards the center of the circle is going to be the normal force. And I can make that into this light blue color, okay? So Fn. So because the weight force acts downwards, the normal force is the only force that acts towards the center, and then therefore, in order to provide a net force, and therefore an acceleration, the normal force has to overcome the weight force, and therefore it has to be much larger than the weight force, okay? Because as you know, if we have a weight force acting downwards, let's say it's this big, okay? And then we have our normal force, which is this big, we know in red, this is our net force, okay? Now, on the top scenario, the weight force is actually acting towards the center of the circle, and therefore it can provide some of that centripetal force. And so the normal force in this case is allowed to be much smaller. And so putting these diagrams into words, we can say at the bottom, our centripetal force is equal to the normal force minus the weight force, okay? And therefore, our normal force is equal to the centripetal force plus the weight force, okay? And at the top, our Fc is equal to our normal force plus the weight force, okay? And therefore, our normal force is equal to our Fc minus our weight force. So again, as I stated in the start of the question, our normal force is what provides us our sensation of weight, and therefore, the greater the weight force, the more heavier we feel. And as you can see at the bottom, our normal force is larger than at the top, and therefore, at the bottom is when we feel the most weight. Again, you can't just write this and get the full marks, you have to write it in words, alright? So calculate the speed that the car must go at the bottom of the loop such that it can go around the vertical circle and seem weightless at the top, okay? So again, this is the concept of minimum speed, okay? Again, if you don't understand that, watch my vertical circles video. From that video, we should know that our weight force should be equal to our centripetal force, and therefore our mg is equal to mv squared over r, okay? And so therefore, cancelling out our masses, we get g is equal to v squared over r, and therefore our v is equal to square root gr, okay? And therefore, our velocity is equal to the square root of 9.81 times our radius of 0.25, and that gives us a velocity of 1.566 meters per second, okay? So that is the speed that we must obtain at the top of the loop, okay? And so at the end of the day, this is a conservation of energy question. So therefore, the energy at the bottom must be equal to the energy at the top, okay? Now at the bottom, we have purely EK, okay? So purely kinetic energy, right? Because we can take this line as h is equal to 0, okay? And so therefore, at the top, we have some EK, plus some gravitational potential energy. So now that we know the velocity at the top of the loop, right, the minimum speed, we can calculate our EK, okay? Because we know the radius of the loop, right, therefore in this loop we have two radiuses, right, because the radius is half the circle. And so therefore we know the height at which this loop is at, so that we can calculate the EP, okay? And therefore, because we know the energy at the top must be equal to the energy at the bottom, because we know the energy at the top, that must be equal to the energy at the bottom, and because we know that EK is equal to half mv squared, we can rearrange for our velocity to get our velocity that we must require at the bottom of the loop. So let's go through that right now. We can calculate the kinetic energy at the top, and that's obviously equal to half mv minimum squared, right, the minimum speed, which we can label that as minimum speed, okay? And we get half times the mass of the car, which again is still 0.120, times our minimum speed squared, which is 1.566 squared, and that gives us kinetic energy at the top as 0.147 joules, okay? And we can calculate the gravitational potential energy at the top as well, and that's obviously equal to mgh. We know the mass of the car is 0.120, right? Hasn't changed. And obviously the acceleration due to gravity is 9.81. Our height is 2 times the radius, which we know is 0.25, I believe, yep. And that gives us a gravitational potential energy of 0.5886 joules, and therefore the total energy at the top is equal to 0.147 plus 0.5886, and that gives us a total energy at the top as 0.7357 joules, okay? And so, as discussed previously, the energy at the top is obviously equal to the energy at the bottom, right? So E total top is equal to E total bottom, and we know that the total energy at the bottom is just purely our EK at the bottom, and therefore, as we know, EK is equal to half mv squared, and so therefore 0.7357 is equal to half times our mass, which again is 0.120, times our velocity squared, which is what we're trying to find. And so therefore 2 times 0.7357 all over 0.21 is equal to our velocity, and obviously we can square that. And this gives us a velocity of 3.5 meters per second. There we go. Tane works weekends unloading barrels. In one instance, he rolls an empty barrel of mass 5.5 kgs with a radius of 0.28 meters down a ramp that is 1.3 meters high. The linear speed of the barrel when it reaches the bottom is 3.4 meters per second. Describe the energy changes that take place as the barrel rolls down the ramp. So at the top, we have purely gravitational potential energy, and then as it rolls down the ramp, our EP gets converted into our linear kinetic energy plus our rotational kinetic energy, okay? And we can label that linear here. Linear and then rotational. There we go. Okay, calculate the rotational inertia of the barrel. Can assume no energy loss due to friction. That's nice. So as discussed up here, our EP at the top will be equal to our EK at the bottom, which is linear, plus our rotational kinetic energy at the bottom. So first we can calculate our EP at the top, and that's obviously equal to mgh. The mass of the barrel is 5.5 kgs times 9.81, which is the acceleration due to gravity, times our height, which is 1.34 meters. Okay, this gives a gravitational potential energy of 72.2997 joules at the top. Okay, now we are given our linear speed of 3.4 meters per second at the bottom, and so therefore we can calculate our linear kinetic energy at the bottom. We know that's half mv squared, so half times the mass of the barrel, which is 5.5, times our linear speed, which is 3.4, and that's squared, and that gives us a linear kinetic energy of 31.79 joules, okay? And so therefore, as our EP is equal to our linear plus our rotational, we can say that 72.2997 is equal to 31.79 plus our rotational kinetic energy, and so therefore 40.5097 is equal to our rotational kinetic energy, right? And we know that our linear kinetic energy is half I omega squared, and we should also know that our omega is equal to our velocity all over our radius, and we have a velocity of 3.4 and our radius of 0.28, which Okay, that gives us an omega of 12.42, okay, radians per second. And so now we can just rearrange for I, and we should get the answer. So we have 40.5097 is equal to half I times our omega, which was 12.14 squared. So 2 times 40.5097 all over 12.14 squared, and that gives us a rotational inertia of 0.54947 kg meters squared. Now, if you look at the marking schedule, it would say that the rotational inertia is 0.553 kg meters squared. However, I believe my answer is correct because I used whole values and they didn't, so I would trust me more than I would trust NCEA. Tane sits on a swiveling stool holding a full bottle of water in each hand. He notices that when he holds the bottle with his arms stretched out, he tends to spin more slowly compared to when he brings his arms inward, close to his body. Explain the reason for this observation. Alright, so assuming that there is no external torques applied, angular momentum is conserved. Alright, when he holds his arms outwards, his effective radius is going to increase. If you don't understand what effective radius means, in my rotational motion videos, I can't remember if it's part 1 or part 2, I go through what effective radius means. But because we know that our rotational inertia is directly proportional to our mass times our radius squared, if our effective radius is increased, therefore our rotational inertia must increase, okay? Therefore, as our angular momentum is equal to our rotational inertia times our angular velocity, again, as stated in the beginning, our angular momentum is conserved and therefore remains the same. If our rotational inertia increases, therefore our angular acceleration must decrease. So when he puts his arms outwards, he rotates slower. However, when he brings his arms inwards, his effective radius is decreased now, and therefore his rotational inertia is going to decrease. Therefore, as his rotational inertia has decreased and his angular momentum remains the same, his angular velocity will increase. Okay? And so therefore you need to explain that in words. Tane spins with an angular velocity of 3 radians per second when his arms are stretched out. When he brings his arms in, his angular velocity increases to 7 radians per second in a time of 4.5 seconds. Calculate his angular acceleration and the number of revolutions he has made in this time. So first of all, it's not stated in this, but we are assuming a constant angular acceleration. It's only if you do physics in university, let's say for engineering, is when you would look at a non-linear acceleration. But for all of NCEA physics, acceleration is constant, okay? And therefore, because acceleration is constant, we can obviously use our kinematics. So our omega, finally, is equal to our omega initially, plus our angular acceleration times time, okay? Now we know our final angular velocity, which is 7. We know our initial angular velocity, which is 3. And we're trying to find our angular acceleration, and we know the time of 4.5 seconds. So we can just simply plug that in, okay? So we get 4 is equal to alpha times 4.5, okay? And that means 4 over 4.5 is equal to our angular acceleration, and therefore we have an angular acceleration of 8 over 9, or 0.889 radians per second per second. There we go. Now to calculate the amount of revolutions, we obviously need to calculate our theta value, and so therefore we can use the equation omega f squared is equal to omega I squared plus 2 alpha theta. Again, we know our final angular velocity is 7 squared, and our initial angular velocity is 3 squared, plus 2 times our alpha, which we found was 8 over 9. The reason why I'm using 8 over 9 rather than 0.889 is because I want to retain whole values, okay? And that's times our theta, which is what we're trying to find. So 49 is equal to 9 plus 16 over 9 theta, right? And therefore 40 is equal to 16 over 9 theta. And therefore 40 divided by 16 over 9 is equal to our theta. And therefore 40 times 9 over 16 is equal to theta. And so therefore we get 22.5 radians is our theta value, okay? Now it didn't ask for the amount of radians that it turns to, it's asking the amount of revolutions. We know that in one revolution we go through 2 pi radians, and so therefore 22.5 all over 2 pi gives us the amount of revolutions, and this gives us 3.58 revolutions, okay? There we go. Tanya is studying the motion of a toy bouncing up and down at the end of a spring hanging from a ceiling. The spring has a spring constant of 24.6. Tanya draws the acceleration against displacement as shown below, and the toy is bouncing up and down in simple harmonic motion. Describe how the gradient of the graph relates to the frequency of oscillation. Okay. So we should know that our omega is equal to 2 pi f, okay? And in this case, our omega is omega squared, and so therefore omega squared is equal to 4 pi squared f squared, okay? And as we can see, this gradient is linear, and therefore we should remember from our math courses that if we have a linear gradient, that means the gradient is constant, right? We should know that because if we differentiate a linear graph, we get a constant number back, right? And so therefore, as our angular acceleration is the gradient of this graph, and because we can tell that this gradient is constant, therefore our frequency must be constant, because obviously 4 and pi don't change, right? Those numbers are never going to change. Those are constant numbers. And so the only thing that can change is our frequency, and because our gradient is constant, therefore the only thing that can change doesn't change, and therefore our frequency is constant, okay? And so from this we can say our frequency is constant, alright? By calculating the gradient of the graph, show that the period of oscillation is 0.199 seconds, and therefore determine the mass of the toy hanging on the spring, okay? So the gradient of the graph is equal to, and so to calculate the gradient, we can take 1 point as the origin, so we obviously know the origin is 0, 0, and we can take another point, let's say right here, and that point is 0.01 and negative 10, okay? And we know that the equation for the gradient of a graph is y2 minus y1 all over x2 minus x1. So therefore we have 0 minus negative 10 all over 0 minus 0.01. And that gives us a gradient of negative 1000, okay? And again, it's just negative because it's going down this way rather than going up this way. So therefore, we're just interested in the absolute value of that, so we can say our gradient is 1000, okay? And we established up here that our gradient was omega squared, so therefore omega squared is equal to 1000. And again, we established up here that omega squared is 4 times pi squared times f squared. And so obviously omega is equal to 2 pi f omega squared, 4 pi squared f squared, and we also know that our frequency is 1 over t, and so therefore our omega squared is also 4 pi squared all over t squared, okay? And this is again 1000, sorry, not 100. So therefore we can plug this into here and we get 1000 is equal to 4 pi squared all over t squared. T squared is obviously equal to 4 pi squared all over 1000, and so therefore t is equal to the square root of 4 pi squared all over 1000. And this gives us a t value of 0.199 seconds. There we go. So that is our t value. Now to calculate the mass, we know that the period when we have a mass on a spring is equal to 2 pi square roots mass all over the spring constant. And so therefore 0.199, again, use the whole value. This is a rounded value, so in your calculator, use a whole value in this situation, okay? And that's equal to 2 pi square root mass, which is what we're trying to find, times our spring constant, which was 24.6, okay? So now rearranging, we get 0.199 all over 2 pi. That's equal to the square root of mass all over 24.6. We can square both sides to get rid of that square root squared. That's equal to mass all over 24.6. And then we can times both sides by 24.6, and that should be equal to our mass. And therefore the mass of the toy is 0.0246 kgs. There we go. Tanya then pulls the spring down through a distance of 0.1 meters from the equilibrium position, then releases it so that the toy bounces up and down in simple harmonic motion. By use of reference circle or otherwise, calculate the time the toy on the spring would take to travel a distance of 0.14 meters up from its release position. Okay, so let's draw another reference circle, and we can do it in quarters, like so. So we brought it down 0.1 meters from its equilibrium position, right? Therefore, this distance right here is 0.1 meters, okay? And we want to know how long does it take to travel 0.14 meters from its release point, so therefore this distance right here is 0.04 meters, okay? And therefore, because it's released from over here, and then we obviously track it in the anti-clockwise direction. Again, if you are not familiar with reference circles, highly recommend my reference circles video that I have. Again, I think it's on my mechanics playlist, okay? But again, with reference circles, we track anti-clockwise, and therefore we would end over here. We can therefore make a right angle triangle like so. This angle is 90 degrees, and we can call this angle theta, okay? Now, as we established previously, our radius is 0.1 meters. Okay, so that's our radius. And let's draw out that right angle triangle to make it easier to work with. We have our theta here, our 0.1 meters, and this distance right here is equal to this distance, and so that's 0.04 meters. And therefore, to find our theta, we can use our inverse sine relationship, 0.04 all over 0.1. This gives us an angle of 0.4115, and that's in radians. Now remember, always work in radians when you're using the reference circle. So that's our theta value. However, that is not the total angle that our toy has turned through. We started from over here, and then we progressed all the way up here. Therefore, we travel this entire angle, which we can call phi. Okay? And as you can see here, as I stated before, we have a right angle triangle right here. And so therefore, our phi is equal to 90 degrees plus our theta. And then to put that into radians, we have pi over 2 plus our theta, which was 0.4115. And therefore, our theta is 1.98 radians. Okay? Now, as we know, our theta is equal to omega t. Now, remember, in this case, just remember, though, that in this case, our angle is not theta, it's actually phi. So our phi is equal to omega t. And therefore, our t is equal to phi all over our omega. And we also know that our omega is equal to 2 pi all over our period, right? We have a period of 0.199, right? And so therefore we can make that substitution into here. And so therefore our time is equal to phi, which was 1.98, all over our omega, which is 2 pi all over 0.199. And that gives us a time of 0.0628 seconds. There we go. Tanya notices that once she has pulled down the toy and it starts oscillating in simple harmonic motion, the amplitude gradually decreases with time and eventually the toy stops oscillating. Okay, let's take the name of this phenomenon and explain what causes the amplitude to decrease. And using the axes below, draw a graph of the amplitude against time for 3 complete oscillations, and also label the diagram. So this phenomenon is called damping, and this is when the period remains the same. However, the amplitude decreases as energy is lost to its surroundings through friction. All right, and so for 3 complete oscillations, we can make one over there, one over here, and one over here. So we can call this T1, T2, T3. Okay. Now we know Tanya pulls it down to an amplitude of 0.100, okay, meters. And so on the other side, that's going to be negative 0.100 meters, okay? And so again, as it states up here, I think, Tanya pulls the toy down to 0.1 meters. So therefore we start at max displacement, okay? We start at max displacement. And in most exams, they usually give you a grid. However, in here, they haven't given you a grid, so it kind of makes it hard. However, the idea is that every time we complete one period, we make the amplitude slightly less, okay? So we can start up here, and let's say we end, let's say over here, okay, and then we'll end over here, and then over here, and then let's say over here. And so if we follow that, we get something like this, okay? And then we should get a shape that looks like this. So it kind of goes like that. All right, and we're done.